Hello all, welcome back to the Interpretability tutorial. In this tutorial, we will focus on studying codebook models trained on algorithmic sequence modeling dataset called TokFSM. Okay. So, previously we were using codebook features in the last tutorial, and we use the same codebook features library here and look at some interesting implications. So, we import all the necessary libraries from the codebook features and we set the gradient to false for as we are just doing the inference here and we are not training the model. Okay. So, the TokFSM dataset is created using finite state machine. In this case, which it consists of 100 states. So, each of these states has 10 randomly chosen outbound neighbors, meaning each state can transition into 10 other states. Okay. To build the data set, sequence of transitions between these states are generated first. For instance, if the sequence is moving from 18 to 0, from again 0 to 39, so the sequence is noted as something 1800 something, like if it is moving from 18 to 18 to 0 and from there to 39, it is stored as 1 comma 8 comma 0 comma 0 comma 3 comma 9, something like this. Okay. So these sequences are used to train neural networks, helping to evaluate how well networks can predict the state, predict the next state of sequence of states in the finite state machine. Okay. Here we define we use GPT-NEO-X model where we define first all the hyperparameters that is required. As said before, we use 100 states and 10 edges here. The sequence length will be 128 and the run name for this particular thing would be hooked model NEOX. Okay. We take all these parameters from this particular dictionary, hyperparameters. We apply it to the GPT-NEO-X model, and like we have done in the previous tutorial, we will wrap this codebook with the existing model and the pre-trained codebook model, and we store it to the CB model. Okay. Once this CB model is, we set this CB model to eval, saying that we don't train this model, we only use it for the generation, for the evaluation. Okay. We use the same CB model to generate a hooked model. We keep everything, we keep every parameter false, so that we don't have any change in the original CB model and the hooked model. Okay. We use this convert to hooked model for TokFSM function from the models that authors have proposed in the codebook features library, and we convert the existing original CB model to the hooked model. Now we have the hooked model and the particular tokenizer that is used for the hooked model. Okay. Here we download the FSM model which is stored in fsm.numpy file. This is a numpy file, and we use this particular FSM to generate the state sequences and all. Okay. So, here train FSM model loads the FSM model saved in the fsm.npy file, and representation base parameter likely defines the number of possible symbols of states in FSM based on the vocabulary size -1, and seed is set to 42 to ensure reproducibility and to stop the randomness of the model. Okay. The token FSM dataset, this class is designed to handle tokenized FSM data. It creates a sequence of states or tokens that model can learn from. After this, we print all the we print all the details of FSM, number of states, number of edges from every state and all. If you observe here, the number of states is 100, the number of edges from every state is 10, and some random trajectory in finite state machine is from state 8 to 53 to 75, 61 and 2. As I said earlier, these are tokenized like this. 8 is tokenized as 0, 8, 53 is tokenized as 5, 3, 75 as 7, 5, and so on and so forth. Okay, this is how the input to the model look like this is the trajectory that we are going to use, and this is the TokFSM data set. It looks like something like this. Okay, this function computes the accuracy with which the model represented by the hooked model here correctly predicts the first transition between states in FSM. The accuracy of the first transition is 97.5%. Yeah, it is decent. Okay. Next, we check the code purity. By pure, I mean how closely the codes are associated with the single input. For example, if the code is 0 and the corresponding transitions is 0, 0 and 0, 1. And let us take this example. If code is 1 and its corresponding transitions is 1, 1 and 1, 2. Okay. And if code is 2 and the transition is 2. Okay. The key thing here is to understand is that pure code is one that is associated with only one output. So, here code 2 is associated with only one single input. Okay, and where code 0 and code 1 has multiple inputs, but code 2 has only one input. So, the total purity, if the layer only has these 3 codes and this is what the network is made up of, then the purity of this code 2 becomes 1 by 3. Okay, because there are 3 codes and this is 1 by 3, and these 2 codes are not pure. We don't consider these 2 codes and we only consider this code. Okay. To check this code purity, first we declare this layer purity bigrams and layer purity trigrams list, so that we can append all the values to calculate the code purity later. Okay. So, here for each layer, this code does 2 things. The two things for bigram and also for the trigram. Okay, it partitions the input space for bigrams using this function partition input space with codebook function, and which gives us a dictionary partitions 2. Okay, where the keys are in this dictionary, the keys are the codes and values are the sets of bigram inputs associated with each code. Okay, now it counts the number of pure codes in partitions 2. These are the codes that are associated with only a single bigram input that we have discussed before. The code divides the count by total number of codes to get the purity of bigram codes for that particular layer and appends it to the layer purity bigrams list. Okay, and the same thing is occurring. So, this partition 2 and layer purity bigrams is for the bigrams, and partition 3 and layer purity trigrams is for the trigrams. So, bigrams, I mean that it is 0, 0, 0, 1, 0, 2. By trigrams it is 0, 0, 1, 1, 1, 2, something like this. Okay. So, this is the code for representing in a visual pattern. Okay. So, if you observe at layer 1 MLP, the levels of purity for both bigram and trigram inputs are very high. Okay. This is because the number of hidden states in the model is 128, but there are 1000 possible trigram combinations for the model to learn. 100 into 10, there are 1000. Since the number of hidden states is less than the number of possible trigram combinations, the network cannot allocate a unique neuron for each possible trigram. But however, the high purity of the codes at layer 1 MLP shows that codebook training has mostly resolved the superposition problem at this first layer. Okay. Superposition refers to the issue where multiple input get mapped to the same hidden representation, making it difficult for the model to distinguish between them. So, as you move to the higher layers, the code purity starts to decline. This is because the model is forming its prediction of the next token, and the codes need to represent more complex features beyond just current state. Okay. Okay. Now we see the next part, steering the network by intervening on the state codes. Okay. This part of code, we see how much the codes learned from by the model influence the probabilities assigned to the different outputs. So, imagine we have a finite state mechanism where it is numbered from 0 to 9. The valid bigram input pairs will be 0 1, 0 2, 0 3, to 0 9. Okay. So, code starts by generating all these valid bigram inputs along with random prefixes for each of one. So, for example, the valid input for this prefix for 0 1 it will append some 5 4 3. Okay. For it something 6 7 8 for 0 2. Okay. So, it adds the random prefixes for each of the valid input that we are saying. This code does all that. Generate all valid inputs with prefix, generated all the valid inputs, all the valid bigrams and diagrams, and we also add the random state prefixes to the generated valid inputs, and we return all of them back. Okay. Then we calculate the JS divergence here. Okay. Let's see some of the parts of this code. There is a main part of testing that we are doing, because we add some random generated code and we see if if it has any impact on the output probability distribution, which we hypothesize that it should happen. Okay. So, FSM here is the finite state machine object. Each trigram is a boolean indicating whether the sequence should be trigrams or bigrams. So, the prefix random states length is the length of the random state prefix to be added to the each valid input, and seed is set for avoiding the randomness. So, here in this function, in this particular line, checks that prefix random state length is valid within the valid range of 0 and 63. To produce the same results as the paper, we have to set this to 62, but here we use it as 0 only. If this is not satisfying, it returns an error. It returns an assertion error here. Reverse FSM creates a reversed version of FSM where transitions are reversed. This is used to generate valid state sequences backward. RNG is a random number generator with the given seed to ensure the randomness is consistent across all the runs. Repeat sets the number of characters in each sequence to 3 if it is trigram, and if it is not trigram, it sets to 2, which is bigram. Chars is a list of all possible digits based on FSM base, finite state machine base. For example, if representation base is 10, then the chars will be from 0 to 9. All valid inputs. Here what we are doing is we are finding the list that comprehensively generates all possible combinations of characters with the length of either 2 or 3 based on the repeat, and filters them to only include valid sequences as defined by the FSM. So, if repeat is 2 and the FSM representation base is 2, which is binary FSM, all valid inputs might include sequences like 0 0, 0 1, 1 0, 1 1, but only keeps one which is valid according to the FSM rules. Okay. So, start states extracts the string of each valid sequence by converting the sequence to a trajectory in the FSM. If sequence 0 1 starts with 0, then start states would be 0, something like that. Okay. Random state prefix generates random state sequences which are prefixes of length that we have defined, prefix random state length for each state used by reversed FSM. These prefixes are reversed and they are converted to the integers. If prefix random state length is 2 and the FSM generates the prefix 3 1, it will reverse it to 1 3, something like that. Okay. Prefix to hide randomly selects how much of the prefix to hide for each sequence. This value is chosen from 0 to the prefix random state length that we have given, which is also 0 here, but this is usually measured from 0 to the prefix random state length. So, here we compute the position in the sequence where the final token appears after adding the prefix. If random states length is 2 and random prefix to hide is 1 and repeat is sum 2. So, we will have the answer as 4 here. So, this is used to convert to a PyTorch tensor for to use in this model, so that model only understands tensors. So, random state prefix here it converts the remaining prefix after hiding back to the string, and here in the all valid inputs with prefix we concatenate each prefix with corresponding valid input sequence. Like if random state prefix is 1 and the all valid inputs is 0 1, then all valid inputs with prefix would be 1 0 1, because 1 is random state prefix and all valid inputs is 0 1. We will concatenate like it will become 1 0 1. Here we use the tokenizer to convert the sequences into token IDs suitable for the input into the neural network, padding them to the same length and converting them to the PyTorch tensor. So, here f dot pad pads the tokenized sentences by adding a beginning of sentence BOS token at the start. Okay. So, if the tokenized sequence is 101, it adds BOS in the start which says BOS 101. Okay. And we set everything to the device in the last to use GPU. So, we calculate JS divergence and all state info is stored in this particular dictionary. JS divergence is stored in this particular dictionary. Okay. Here we calculate using JSD from CB utils. JSD is JS divergence. We calculate the JS divergence between the input sequences and the output probability distribution. So, here we calculate the JS divergence between the output distribution of all pairs of valid inputs. For example, it calculates the JS divergence for the output distribution for 54301 and the output distribution for 87602, where 0102 are the bigrams and 543876 are the appended random prefixes. Okay. This part of code evaluates the impact of different model patching configurations on the model's output by measuring how changes to the model's internal codes affect its predictions. So, it calculates the JS divergence between the output distributions of modified and unmodified model states. Okay. So, we define patching to plot here, which is none, where L0 attention defines that patching at layer 0 for the attention, and we are here L1 MLP defines that patching at MLP layer at layer 1, MLP layer 1. Okay. This defines all the attention layers and all the MLP layers, and all attention and MLP layers included, not individually, everything included. We declare a dictionary, JS divergence for patching, a dictionary where we'll keep track of JSD values for each patching configuration. Initially, this is set to 0. Then we go over a loop with each input and its particular index. For example, if all valid input contains 0, 1 and 1, 0, you process each one separately. For each input, we compute how different its prediction is from all other inputs predictions using JSD. This measure will help us to understand the impact of changing one input on the model's predictions. Okay, so we do a little adjustment here, JSD adjustment, divide the number of states minus 1. Yeah, and after that we divide by the number of states minus 1. This ensures that self comparison JSD between the same state is excluded since it's always 0. Okay, JSD of B comma B, the same two states, is always 0. We loop over all the patchings in the patching to plot, where if the patching is done, we will continue. But if patching is something like patching is this here, none L0 attention. So here we have the underscore, and we take the word after the underscore. That's what this CB at does. Okay, layers determine which specific layers need patching based on the configuration. Heads, if attention layers are patched, create a list of attention heads to be affected. Example, from 0 to the number of heads minus 1. Okay, so here we, if it is the attention, then we do these operations on that particular attention layer, and CB at rep and heads rep, these two variables replicate the list of configuration and heads for all layers to ensure the consistency. Okay, layer representation, we create a empty list here first, and this meant to create list of layers to patch based on the configuration. From cache B, we get all the current model raw logits and activations for the given input. Then here we extract the necessary code, logits and activations both for the specified layers and the components. So now we have the modified logits and modified cache. We use this and compute the JS divergence between the modified and the original ones. Okay, so here we measure the JST between the modified logits and the original logits, adjusting for the self comparison. Okay, here we add the computed JSD for current patching configuration to the dictionary, and we plot everything in a. So the idea is to see how much the learned codes at different parts of the model, attention, MLP, influence the output distribution. If modifying the codes for one output has a large effect on the output distribution of the another input, it suggests that those codes are playing a significant role in model's decision making process. We visualize this with the bar chart here. So next, we move to the next part, inputs grouped by the codes. Here we want to test whether the states grouped together by codes in latent layers of the codebook model have more similar output distributions compared to the randomly selected states. This will help us understand if the model group states together because they predict similar next tokens or something. Our initial hypothesis is that states grouped into the same code, that is those that share a code in the model, have output distributions that are more similar to each other than those of the randomly selected states. the similarity would be reflected in a small divergence value between states grouped by the same code compared to the randomly selected states. We compare the divergence between output distribution of states grouped by the same code with the divergence between the randomly selected states. So we go through this code. Chars, this creates a list of characters representing all possible tokens that are taken from the representation base. All valid inputs too. Here we generate all the valid input combinations of length 3 using the character iter_tools.product, which creates a Cartesian product of characters of length 3. FSM utils.valid input ensures the combination is valid across according to the FSM finite state machine. So, this particular function iterates overall valid inputs and computes the logits and cache for each input using the hooked model. All state info stores the logits and cache for each input in all state info dictionary. In similar way, JS divergence to here, it calculates the JSD between the logits of input A and input B, and it stores in the dictionary JS divergence too. So, this measures the divergence between the output distribution of two inputs. Okay. We iterate over each layer of the model, compute how inputs are grouped by a code in specified layer component, which is MLP in this case, and the codebook index. We use all these divergence metrics and all these values to plot the JS divergence between trigram input pairs and trigram input. If you see in the layer 1, trigram input code pairs have they have the little JS divergence, but if you see in the layer 2 and layer 3, they are getting grouped each other, but trigram input pairs are not. They have more JS divergence as the layer increases. Okay. So, from the above plots we observe that the trigram inputs that are grouped together have a significantly smaller JS divergence than the random trigram input pairs which supports our hypothesis. So, in the to wrap all these things up, we have seen that all these codes that authors have described in the paper have the significant effect on the output distribution, and these codes can be used to steer towards a particular topic and get the desired outputs.